Hi, all right, so welcome back. We kind of stopped in the last video after we introduced forward neural networks. We've been taking a look at what are neurons, what is a layer, what is an activation function, and how do you generate neurons for a new layer given you have neurons from the previous layer. And yeah, basically we've been talking about the mathematical operations that are always repeated to generate neurons for a new layer out of the neurons from a previous layer. So if we continue here with this, what needs to be said further is to define a full forward pass through a neural network, or to define a forward neural network, then even though like you can do this process that we've been describing in the previous video as many times as you want. What will happen is that you, for instance, once you started with the input layer, so the original variables, and you created, as in our video, for instance, out of 3 input variables, 2 hidden neurons for the next layer. Then this next layer is usually called the hidden layer. In our case, that would be the first hidden layer. You can now treat those neurons in the hidden layer exactly in the same way as you treated the input neurons from the previous layer. So that means you can again, use those mathematical operations to combine the hidden neurons, the neurons in the hidden layer, again with this exact operation that we've seen before here. So with this, weighting, so give a weight to the first hidden neuron for the first observation, and a weight, for instance, to the second neuron for the first observation, add a bias term, and then you create another number, and then you put that into an activation function, and voila, you created another neuron which is considered to be used for the next layer. And you can make different choices here. You can use a different activation function. You can choose now to create a different number of hidden neurons for the next layer. So this is really flexible, and I think this is also one of the key characteristics for the great success of neural networks, because they are so flexible. But basically it still will be always the same. Okay, so you have the previous layer with hidden neurons. You make the decision, okay, how many neurons do you want to create, which type of activation function do I want to use, and then you combine these two mathematical operations, basically matrix calculation, and then inserting this output into an nonlinear activation function, and then collecting the new crafted hidden neuron. However, for, I would say, the plain or like vanilla for neural networks, usually you will not see more than 2 or maybe 3 hidden layers, because if you would use more, then you very likely or often run into mathematical problems when you train such a network. This is not something we discussed so far, but like the buzzwords here would be like the vanishing gradient or exploding gradient problem. So I would say it's very common to observe forward neural networks with like 1 or 2 hidden layers. And then lastly, the last, when do you stop? When you stop, usually the last layer is called the output layer. And it kind of depends, especially in the example we are using here. And I would say in general, if you have any kind of supervised learning task for a machine learning problem, for instance, so that means you have a certain target variable for which you would like to make predictions. This kind of defines the dimensionality and also the activation function for the output layer. Okay, so for instance, for the real estate example, you usually want to create one real valued number for every observation in a data set, and then you would treat this real valued number as the prediction for the real estate value of the corresponding real estate. So that means in the last output layer, you will always would choose to create only a single neuron for every observation. However, as we will see also in the videos that are following, for instance, if you have a classification problem with multiple classes, so that means your target variable could be, for instance, the reaction of the customer is negative, neutral, or positive, then maybe you would create 3 numbers for every observation, each number, for instance, corresponding to the probability that this observation is corresponding to a certain category here, okay? But we're going to take a look at this later. Just saying here at this moment, usually the only thing which is fixed in terms of number of neurons is then the task itself sometimes defines the dimensionality for the last layer, and also the activation function. Because, for instance, for real estate, you basically want to have a real valued number. For real estates, maybe it's only useful if they're positive, but You may still would then just use what is called the identity activation function, which just returns the same number which is used as the input for the function. However, for instance, for classification problems, very often we use a transformation or activation functions for the output layer, such that the numbers that are given can be interpreted as probabilities. So that means they must be between 0 and 1, and in case of multi-class classification problems, they need to add up to 1, right? Okay, but now for our example, what we take a look here, and also this is a slide or like a very superficial introduction into pytorch. What we have here is we have this module, which is the base class here, and then you can define our own class in pytorch. And here in the beginning, when you initialize an instance of this class, here we can set the mathematical functions, operations that we're going to need to define our forward pass. And here then we have the forward method, which is defined, which is then later on called by the call method of an instance of the class. So that means if you take a look here, the NN linear is something you've seen in the last video already. So that is just the matrix operation. And then we have here also an activation function again, which is the relu function. So this class here would always define a neural network that has a single hidden layer with the relu activation function for the hidden layer. And as you will see here below, the identity function for the output layer. The only thing that you as the user would define here is the input dimension. So what are the number of input neurons, how many hidden neurons do I want to create, and what are the number of output neurons that I need, right? So these three numbers. And if you take a look here through the forward pass, so first the input x here in our case would be looking like something like that here. So we've seen that above. So that would be a batch of the data or the whole data sample. And then what we have here is, the matrix operation. Then we activate this with the relu function. So these are the hidden neurons for the second layer. And then we conduct again another matrix operation, but leave them as they are. So technically using the identity function, which are now our neurons for the output layer that are here returned by the forward method. All right, and this is basically it, how you would define a simple forward neural network with pytorch here. And first, before we use it here, one last thing. I always found it very helpful when I started learning about neural networks to think about, okay, what is the number of parameters that we would need for a forward neural network given certain dimensions for the input, the hidden, and the output neurons here. Because I think if you have this, then you kind of understand the forward pass. So for instance, in our example, if we have 3 input variables, we want to create first 2 hidden neurons for every observation, and then 1 neuron as in the output layer. What do we need, right? So what are the number of parameters to come from the input, which is 3-dimensional, to the hidden layer, which is 2-dimensional, and what are the number of parameters that we need from this hidden layer to the output layer, okay? So maybe you want to think about this for a second and pause this video if you don't, all right? Then what we would have is, of course, when we want to create first out of 3 variables, 2 neurons, we need 3 weight parameters each, so 6, and we need 2 bias parameters, so 8. You can take a look here also. This returns the parameters that are here initialized in the model in the beginning. So this is the transformed version of it. So that means that would be the weights for the first hidden neuron. That would be the weights for the second hidden neuron. This is the bias for the first hidden neuron. This is the bias for the second hidden neuron. And then at this point, we have, like, for each observation 2 hidden neurons, and to bring them to 1 number again, we need 2 weights and 1 bias. Okay, so these are then the 2 weights and 1 bias. So overall, you would have 6, 8, 10, and 11 parameters. Okay, so now maybe as a practice, you can also, for instance, change this here to whatever, 4 and 2, and before you execute, think about it again. And I think once you get this and once you see this, you already have a very good understanding of the forward pass for the neural network. Right, once this is defined, practically how you could then calculate the predictions using the current weights and bias values in the model is simply by calling, or like this is what you do here in a Pythonic way, sorry. You first create an instance. Okay, sorry, switched here. We create an instance of the model here. We tell it, okay, input is 3, hidden is 2, output is 1. And then this is how you call this for the data. And these then are your predictions. Don't get confused that the numbers are so similar here and everything, because that is, we don't operate with real data here. And also in the beginning, all weights, all bias parameters are randomly initialized, so they're all very similar, at least when averaging them or when calculating here the weighted sums. So, and as you can see, every time we create, we call this cell here, we would initialize a new model here, and for every time those weights and parameters would be initialized differently, as I said in the beginning, always randomly. So this is how we have different realizations here. But those would be, at this point in time, the transformation of the input data through the network, and in our case would be then interpreted as as the predictions for the target variable here. And here, last but not least in this video, this is mathematically also in line with the notations from before, what this basically is. And I think if you're used to some kind of notation like this, you can see now in a very good way that really neural networks, especially forward networks, are just a composition of different mathematical operations. And here, at least if you're a little familiar with the matrix operation symbol and here adding stuff, this is how exactly what is done manually internally in this neural network when you call the forward path using the as we can see them here, the linear classes and the activation function here. All right, so this is like a beginning, just that you've seen this for once, how you would define your neural network using pytorch and how you can now use it to go through the forward path. In the next video, we are quickly going to talk about how you now will train the neural network. Training means now you are adjusting the parameters, all you can see here, in a way that iteratively your predictions are always getting better over like an iterative process here. And once you're done with that, you can also then fix and freeze the model and use it for whatever you want to. And in the end of this notebook, which is currently not completely finalized, we are going to take a look at 3 examples how you would simulate and train a neural network for a regression task, such as the real estate example, for a binary classification task, for instance, if you have a target variable that says customer is going to buy the house or not, and also for a multi-class or like a multi-classification task. And especially for the language models, I would say the latter or the last one, the multi-classification task, will be the most important. But this notebook should serve really as a good starting point if you start with neural networks and show you like the basic examples that you have when you would have a supervised learning task. All right, before it gets completely dark in this video, let's end here and then continue in the next video talking a little about how neural networks are trained and then take a look at examples. And then we would be good to go to start with our first neural network based text model. Take care and see you soon. Goodbye.